At first glance, black holes seem to offer the universe a terrifying loophole. Drop a book, a star, or even an entire civilization into one, and every detail that once defined, it appears to disappear forever. The pages, the atoms, the memories, the arrangement of every particle, all of it slips past the horizon and vanishes from the observable universe. According to Einstein's general relativity, this feels almost natural. Gravity curves space-time so severely that nothing crossing that boundary can ever return. But quantum physics refuses to accept that story. In the quantum world, information is not just useful bookkeeping, it is woven into the laws that govern reality itself. The exact state of every particle, every field, every interaction must evolve in a way that preserves the underlying information. Even when matter burns, explodes, or transforms into radiation, the total informational content is never truly lost. It may become impossibly scrambled, but it survives. That is where the contradiction begins to crack physics apart. A black hole seems to promise perfect erasure, while quantum mechanics demands eternal memory. One theory says the universe can forget. The other says forgetting is fundamentally impossible. For decades, these two pillars of modern physics coexisted uneasily, largely because black holes were thought to be cosmic prisons that simply lasted forever. Then Stephen Hawking changed everything. By combining quantum field theory with curved spacetime, Hawking discovered that black holes are not completely black. They emit a faint thermal glow, now known as Hawking radiation, and over unimaginable spans of time, they can slowly evaporate away. This transformed the problem from strange to catastrophic. If the black hole eventually disappears, what happens to everything that fell inside? If the final radiation is only random heat, then every detail about the swallowed matter is erased from existence. That possibility was more than unsettling. It was revolutionary. If true, it meant one of our deepest quantum principles fails in the most extreme regions of the cosmos. And if the universe can truly lose information inside a black hole, the terrifying implication is no longer just about stars collapsing in distant galaxies, but whether reality itself can permanently lose its past. And that question makes every law linking past to future feel far less certain than physics once assumed. Hawking's discovery turned the paradox from a philosophical discomfort into a direct assault on the machinery of quantum law. If empty space near the event horizon constantly seethes with quantum fluctuations, particle pairs can briefly appear from the vacuum. Normally, they annihilate almost instantly. But near a black hole, gravity can tear the pair apart before reunion. One particle escapes to infinity as Hawking radiation, while the other falls inward carrying negative energy, slowly reducing the black hole's mass. And, there we go, this means the black hole is not eternal. It leaks over trillions upon trillions of years. It radiates away its energy and shrinks toward nothing. Classical intuition finds this bizarre but manageable. Quantum mechanics does not. The escaping radiation appears purely thermal, like the random glow from a hot stove. It seems to depend only on the black hole's mass, charge, and spin, not on the infinitely rich details of the matter that originally collapsed or later fell inside. And that is where the paradox becomes devastating. Imagine throwing two completely different objects into identical black holes. A library in one case, a cloud of hydrogen in another. If both black holes eventually evaporate into the same featureless thermal radiation, then the outgoing universe contains no record of which history actually occurred. Different paths lead to the same future. In quantum theory, that is forbidden. The evolution of reality is supposed to be reversible in principle. If you know the final state perfectly, the laws should allow you to reconstruct the past. Okay? Black hole evaporation seems to break that rule. This is not a minor technical glitch. It attacks the deep quantum principle that total probability always adds to 1, and that information is preserved through time evolution. Lose unitarity, and physics loses its ability to guarantee consistent causal structure. The universe stops behaving like a lawful transformation of states and begins acting like a machine that can delete causes while leaving only effects behind. That is why the information paradox shook physics so deeply. It was never just about black holes. It threatened the very logic connecting yesterday to tomorrow. If nature allows true information destruction, then prediction is no longer fundamental, reversibility becomes an illusion, and the mathematical backbone of quantum mechanics may be incomplete at the most extreme edges of space-time. So the crisis sharpens into a brutal question. If Hawking radiation looks random, where could the missing information possibly be hiding? Some physicists hoped the information might remain trapped forever in a tiny remnant, while others argued Hawking's calculation had missed subtle quantum correlations encoded in the radiation itself. Both possibilities preserve reality's memory, yet each demands a radical revision of space-time intuition. The deeper physicists looked, the clearer the contrast became. Either black holes rewrite quantum law, or quantum law rewrites what a black hole is. The modern rescue of the paradox begins with a radical shift in perspective. Perhaps the black hole was never the true problem. Perhaps our picture of space-time was incomplete. In the ideas from string theory and holography suggested something astonishing, that all the information swallowed by a black hole might be encoded not in its hidden interior, but on its event horizon, like data written across a cosmic surface. This became the heart of the holographic principle. Just as a two-dimensional surface can store the instructions for a three-dimensional image, the horizon may preserve every microscopic detail of what falls in. From the outside, Hawking radiation would then not be perfectly random after all. It would carry incredibly subtle correlations, so scrambled that they appear thermal at first glance, yet secretly containing missing history. A black hole complementarity pushed the idea further. To an outside observer, information never truly crosses the horizon. It becomes smeared across the surface and slowly leaks back out through radiation. To the falling observer, nothing unusual happens at the horizon. Both descriptions seem contradictory, yet quantum gravity may allow them to coexist without violation. The deeper implication is extraordinary. The paradox may be telling us that space-time itself is not fundamental. Geometry, horizons, and even the inside of a black hole could emerge from deeper patterns of quantum information. In that sense, black holes did not break physics. They exposed its unfinished foundation. So the true legacy of the information paradox is far bigger than Hawking radiation. It forced physicists to ask whether reality is built less from matter and space than from information itself. And if that is true, black holes are not cosmic erasers, but the places where the universe reveals its most hidden code.